Well, welcome everybody to Hydroterra's latest webinar. This is an exciting one. We're doing this in collaboration with IAH Australia, which is the International Association of Hydrogeologists. And we have two people with me today. We've got Mark Hocking, who's Principal Hydrogeologist from Tetra Tech, and we've got Ben Hall, who's representing IAH Australia's Victorian branch. It's great to have them both here today. I would like to begin by acknowledging that we conduct our work across this great land, and for that privilege, we would like to thank the traditional owners. Hydroterra respectfully acknowledges the Boonwurrung people of the Kulin Nation, where we are located today, and we pay our respects to their elders, past and present. Why do we do our webinars? Oh, sorry, what do we do at Hydroterra? I think this slide's more about. We're all about monitoring, and we have a marketplace of products. We have support for those technologies. We provide field services and we provide monitoring systems. So think of us when you need to do environmental monitoring. Here's pictures of our presenters. A little bit about our presenters. So Mark Hocking, who's going to be doing the majority of the work, is very well educated. In summary, he's got a PhD in hydrogeology. He's got 30 years experience in salinity investigations, groundwater modelling, mining, hydrogeology, and environmental impact assessment. He's worked in the Victorian government in various roles, including as a state government hydrogeologist, manager of the groundwater group in the Geological Survey of Victoria, the Wimmera CMA, and has operated as a consultant throughout Australia. I've got Ben Hall, another doctor. Dr. Ben Hall is a hydrogeologist with 25 years of experience in the groundwater resources, mining and contaminated sites fields. Ben works primarily in consulting and teaches geology and hydrogeology at RMIT University. Recently, Ben was lucky enough to chair the organising committee for the International Groundwater Congress hosted in Melbourne, which was a great success. So very lucky to have two groundwater specialists here today and excited to hear what they have to say. We know you love asking questions and we love your questions. So please make sure you log your questions using the Q&A button at the top of your screen. I will read those questions out at the end of the webinar, and Mark and Ben will do their best to answer those questions for you. Why does Hydroterra do webinars? We like to share knowledge, we like to facilitate education, and we like to take an industry leadership position. I think IAH's values are well aligned with Hydroterra's, so it's great to be doing this in collaboration with them. Without further ado, I'd like to hand over to Ben, who's going to tell us a bit about IAH.
Yes, thanks very much, Richard, and thanks very much for this opportunity to yourself and Hydroterra for creating this opportunity for IAH to help share all things groundwater. Certainly part of our mission is to promote groundwater and sharing knowledge and discussing all sorts of issues that come up in groundwater at different times. As you mentioned, we're lucky enough to, many of you were able to get to the Congress in Melbourne a couple of months ago. That was a great time. And so I've long been involved with these sorts of things. And for those of you out there who are IAH members and have been to our technical presentations, usually in the evenings, they are still going to be happening. We had Alexis just recently give a technical presentation earlier this week. So this is going to be an as well as thing, not an instead of thing. So I'm really happy to be finding another opportunity to host presentations and reach as many people as possible. I think that's probably enough about IAH. If you don't remember, please join up. Very economical membership compared to some other organisations, and it's a great networking and knowledge sharing organisation. So I think that's enough from me. I'll hand across to Mark, and certainly very interested to listen to this presentation coming up.
Thanks very much, Ben.
Thank you, Ben. Well, today I'm going to talk about salinity and groundwater impact assessment, 30 years on, and what have we learned. I'll talk about what we knew back in the 90s, and the reason I'm referencing back in the 90s, it was at the start of my career. When I first walked into the department, what the things that I was told, shown, and then how things have changed to where we are now. I'll talk about the groundwater trends. I'll talk about the tools that we now use, and then I'll just finish off by talking about the MDBA approach of salinity management. The information that I present here is my opinion and my own, and it rides on the shoulders of a lot of other people that have done work over the years. So I'm just summarising this. It's not pretending that anything to do with just me. So as a background, state government groundwater monitoring database, it started back in the 60s when the Geological Survey of Victoria were doing drilling throughout Victoria to understand the groundwater resources and geology and stratigraphy across the state. The construction of the bores, groundwater monitoring bores, really started in the 1960s, and it's provided that baseline of understanding. Today, the Victorian government, DECA, have got more than 220,000 boreholes, and 1,400 of those are actively monitored in one way or another. There is another database of boreholes that exists in Victoria, and that's the Geological Survey borehole database through GeoVic. So if you're interested, go and have a look at that. And also there's the other database that exists parallel to the DECA one is the VVG database. So we're fortunate, and then of course there's the Bureau of Met database as well. So we're fortunate to have a couple of databases where we can source our data from. Next slide, please.
Yeah. Is there commonality in what's stored in them, or they're complementary data sets?
I think the Victorian government database is really about their data and their data alone. VVG picks up other sources of data where it can. For example, the GeoVic data, it incorporates that. I have seen EPA data in the VVG, but I'm not sure if that's in the DECA database as well. So because VVG is a non-government database, it sources the data from a variety of sources.
Thanks.
So just get some context or some terminology or understanding clear. There's two different types of salinity in Victoria. There's primary salinity, so the salinity that occurred prior to European settlement. It's described as natural salinity. There's features in the landscape that we know that exist, such as Pink Lake and Mitre Lake. That's Mitre Lake there looking for Arapiles. And Major Mitchell talked about it in the 1836 when he passes through. Now, there's been a lot of work that's been done about trying to understand primary salinity, particularly on the Dundas with Erica Nathan's type of work. So there's primary salinity, and then the other type of salinity, and the next slide is called secondary salinity. So secondary salinity is the salinity that's occurred following European land clearance and settlement. It's described as induced, and it's caused by the rise in groundwater levels. It also occurs via groundwater discharge in the waterways where that groundwater is saline. There's been a bit of historic research that's been done in the Wimmera. Darryl Strudwick did some historic surveys talking to landholders, and they identified the increase in salinity areas over different climatic sequences or wet periods, and that includes 56, 64 and 73. So 73 is quite a key one, and I'll talk about that later. In the Loddon, Phil McCumber's work identifies in Bears Lagoon that groundwater started becoming artesian in the 70s. So again, in 1973 was quite a wet period. So just to get context, today I'm going to talk about, I'll focus in on Northern Victoria a little bit more than anywhere else, and I'm going to talk about the deep leads. So the deep leads are those ancient tertiary valleys that are backfilled with gravels and sands, and they're high-yielding aquifers, and they provide a pathway for groundwater to move from the the uplands down to the lower lands along the Murray Valley. The image on the bottom left corner is the stratigraphic profile. You can see where it says Calival Formation, and beneath that there's a formation or a group called a Renmark group. The main two aquifers I'll talk about are the Calival and Renmark, but on top of that is the Perilla Sand, and the Perilla Sand is a blanket formation, what I'll call a blanket formation, that exists pretty much to the western side of Victoria in the northwest. And I'll make reference to that later too, just to provide context. Next slide, please.
What's the geology of the deep leads?
So it's a coarse quartz gravel and sand. It's formed in a higher rainfall period. Some work that I did in the Wimmera looked at what type of climate that was. The estimates were that rainfall was 4 times more than what it is now. So it had these massive river systems that were passing down and eroding the landscape. But then as the climate changed, these river systems have backfilled up with sediments to where we are now.
Thanks.
So in the 90s, and I should reference that there's quite a few sources where I come up with this information, and I guess it's the work that's been done previously or historically has really provided a basis to build understanding across salinity processes in Northern Victoria. And one of the key ones there is Phil McCumber's work, the interactions between groundwater, surface water in Northern Victoria. Work by Tickle, and Phil Dawson's also done quite a lot of work in these areas. So in the 1990s, when I started, the trends that were quoted were in the Goulburn Valley, the groundwater levels in the deep leads, but I'll call it the deep leads, were rising at different rates, 15 centimetres a year, Campaspe 20, Loddon 14. All these groundwater levels were rising. And in the irrigation areas, they're also rising. So it wasn't a particularly good picture. Next slide there, please, Richard. So our understanding of the salinity processes in the 90s and via reports and references is that there wasn't seen to be a significant increase in rainfall since 1900 when groundwater levels were first recorded. So it was assumed that the increase in groundwater recharge was associated with land use clearance. So acknowledging that some irrigation practices increase groundwater recharge and cause the shallow water table. So, for example, dry land vegetation, the change from trees to annual pastures, was understood to increase groundwater recharge. High rainfall periods increase the groundwater levels and discharge, but the understanding of what that actually caused or the amount was unclear. And then it was also understood that groundwater salinity increases in shallow water tables via evaporation processes. So the basic concepts were well understood by the time we're in the 90s. Next slide, please. So in the 90s, when I first started, the terms prior to that were trying to fix or stop salinity, and then it started becoming say, well, we need to live with this salinity. We need to just say it's going to be here all the time, from this point forward, and we've got to change our land uses. And here's just a picture that I dug up from somewhere. Obviously, we don't wear similar clothes now, but they've got saltbush in some of their saline areas, and it's really saying, look, let's get some productivity off these landscapes that are very saline otherwise. So we'll go to the next slide there, Richard. So some of the things that really changed from the 90s. So in the 90s, and for those of you that may or may not remember, it was very hard to do a graph. Excel was only just starting to come out. Our computers didn't have very strong processing power. There was very limited ability to provide map products. I used to work on a Sun workstation that was just DOS prompt commands. And then the likes of ArcGIS and QGIS come out, and we could start graphing things in Excel at least. So we had a significant change over the next couple of decades on computing power and different methods. And then also in the late 80s, MODFLOW and groundwater modelling methods started to develop. So it was a real change in what we could actually do with trying to understand groundwater processes. And all these processes were not just DOS prompt. We had these graphical user interfaces or GUIs. So we didn't have to understand coding. We could just click and point and do things. So next slide, please. So with this, it made life a lot easier in a sense. We could make up hydrographs, but in the field, things also changed somewhat. We used to use a fox whistle or a plopper to measure the groundwater levels. Nowadays, we have an interface probe and even data loggers. So the data loggers, obviously, we can record a lot higher resolution information than we can with a fox whistle. And this hydrograph here is just an example of a hydrograph. I'll talk about it in a bit more detail later. But the one thing you can see is in 2023, where there's a significant step rise in the water level, that was actually a flood event. Now, you would have only measured that with a data logger because there was two reasons you wouldn't measure that manually. One, you might not be there at the right time to measure the water level, but also you couldn't get to the site because the site was flooded. So a lot of our historic data hasn't recorded flooding events because we couldn't get access to the bore to measure the water level. And I remember some of those instances when I was in the department is that the people that used to go out monitoring groundwater levels said, "Oh, I can't go today, it's flooded." And you're missing data. So it's just acknowledging that now we can pick up much better data. Next slide, please.
Just to explain the technology, that fox whistle, a lot of you probably haven't seen a fox whistle. It's got a little hole inside it, and when it goes up and down, that's pushing air through that little hole and it makes a whistling noise. So an expert practitioner like Mark be able to get an accuracy of about, what, a centimetre, Mark? Would that get down to that?
Yeah, that's pretty close. Yeah. Yeah. Yeah, it's one of those things you take for granted. You expect people that, yeah, it's fox whistle. So while things started changing in the 90s, the Victorian government, and particularly the agricultural side of the government, were really trying to understand this issue of plant water use and groundwater recharge. So there was a lot of field trials undertaking, looking at perennial pastures and trees and salt-tolerant vegetation, trying to increase the plant water use in the landscape, and thereby, via increasing plant water use, decrease groundwater recharge. And that information was being used both on site to understand vegetation growth rates and potential productivity, but also feeding that information in to try and predict what different recharge rates might be under different land uses and climates. Go to the next slide, please. So this push for groundwater recharge was a strong one, I guess, across Victoria, but across the MDBA or even nationally. And so on the right, I'll go on the right first. There was all those scatter plots are based upon field trials. So this is what's called the Zang curve. So CSIRO through the National Dryland Salinity Program tried to understand under trees versus pastures, what is the difference in plant water use and can we actually make a difference? And so you can see that there's some plots there. And for example, if you're in 800 mil rainfall, a tree is more likely to use 200 millimeters of water more than than if it was an annual pasture. So if we go to the bit on the left, so while that's being done, there was also a variety of soil hydraulic attribution being done to try and understand what the soil properties were, an attribution of that. And at the end of the day is that there was broad rules we could make up with saying that we think that around groundwater recharge is likely between 2 to 10% of rainfall, depending on the land use and depending on the soil hydraulics. And of course, as I said, depending on the climate too. So in a higher rainfall area, you'll get higher recharge. I'll go to the next slide, please, Richard. So a variety of reports that we're getting done. I'll just touch on these quickly. If we go from right to left, there was the likes of BC2C modelling reports, so looking at the biophysical capacity to change of landscapes, where it looks at land use and rainfall and tries to understand predicting what these salt loads or the different changes in water tables that get done. In the centre was the agricultural department's work on the catchment analysis tool. It's really trying to simulate these groundwater recharge processes, and I'll talk about that a little bit more in a couple of slides. And then on the left, more groundwater drilling and process understanding by broad-scale land use changes as examples, and this is just what impact that blue gums were having on groundwater systems. So it's just an example of the type of investigations that used to occur. Next slide. So while we're going through all of this, is that so our GIS ability has increased significantly. So now it's not just specialists using GIS. A lot of hydros could use GIS, and it was seen that the community were quite concerned about salinity. We were telling them that our groundwater levels were rising at quite significant rates. They could see increased land salinity on their farm. And so the concept of the groundwater flow system mapping was done by the likes of Ray Evans, Phil Dyson, and Jane Coram, which was really trying to, as a communication tool for the community to understand where groundwater, if you were getting salinity to location, what that source of groundwater recharge might have been. And you could extend that out across a larger area. And so it also helped conceptualize from a hydrogeology point of view. We could talk to other hydrogeologists saying, oh, that's a local groundwater flow system. It's recharging on the top of that hill and it's discharging just here, rather than saying it's a regional aquifer system that's discharging here and maybe there's nothing you can do about it from an agronomic point of view. So it was quite a useful tool to communicate to the community and to other hydros. Next slide. Now, the next step, of course, was the development of the Victorian, and which turned into the National Aquifer Framework Mapping. So what I call the VAF was, I think it was a major step forward for understanding Australia's, but Victoria's hydrogeology. So it was actually developing a map layers that define the thickness and the extent of aquifers across Victoria. Now, some of the issues we had there, of course, is that with standard naming. So in the example I have here is that the Renmark group, which is the lower tertiary aquifer, compared to the Dilwyn, compared to the Latrobe group. Now, there was a lot of workshops that were undertaken through here to different hydrogeologists having different opinions, and it was finally agreed that the lower tertiary aquifer was a standard name for that. But of course, through these workshops, they were quite heated at times, and as the saying goes, if you have five hydrogeologists in the room, you'll come out with 7 different opinions, and it was definitely the case in developing these things. It was a bit of a push, but it was quite admirable how it got there. So we go to the next slide. So now, I've said to Richard before, I could probably spend an hour talking about the Victorian Aquifer Framework mapping, how it was done, the different names, and what the extent of these aquifers look like. This is just a plan view of these aquifers. If we strip off different aquifer layers, you'll see that other aquifers sit beneath those. So it's actually a truly 3-dimensional framework or mapping system. Now, the significance of that is that it actually then enabled groundwater modelers to say, here's a uniform data layer that we can use for modelling across the landscape that was actually freely available. And that's one of the real strengths, is that it's actually freely available on the internet even now. So we'll go to the next slide, please, Richard. Now, at the same time, while the VAF was getting done, the Victorian government really kept on pushing via agronomists and plant water use modelers and soil mapping people to understand the difference of groundwater recharge and other attributes such as crop yield, runoff, to simulate groundwater processes. So I've circled the one that I'm interested in more than anything else, which was the simulated groundwater recharge. So now we had spatially varying groundwater recharge depending on land use and soil type and climate as a map layer that varied over time. Now, linking that with the VAF work, it's say, well, put those two together and you've got the ability to actually model groundwater processes, because we've got that recharge and we've got the spatial extent of aquifers. So if we go to the next slide, the next step, which logically from what I've just said there, is the eco-markets groundwater modelling. So for each catchment management authority across Victoria, a groundwater model was built, and with the intent to understand the landscape's sensitivity to land use change. So through the agricultural sections of the Victorian government, they could change land use back to the natural, the assumed natural vegetation, or change the vegetation to other types and look at the impact that'll have on the groundwater systems via groundwater modelling. And it was a significant step change in understanding catchment processes. So we go to the next slide, Richard.
Just
Is
before you
you're right.
do, so was this then applied as how to manage the catchments? Was there actually instruction given to land use holders? They had to change crops or plant
Well,
plantations, that sort of thing?
so through eco markets, there was a process to go through. There was some trial areas where landholders were given financial benefits to change their land use, as it was identified to provide a benefit in reducing groundwater recharge and thereby salinity. In a couple of slides, I actually go through in a little bit more detail one of those examples. So I'll just talk on this one for a second. So this is an output for the Golden Broken eco markets model. Now, for the first time, that I could remember, was that the graph on that top left shows the catchment water balance. So this is something very new, and it provided the context of how much the volume of recharge we're getting across the catchment, and then how that groundwater distributed or discharged across the catchment. So base flow and the water exporting by drains, and also groundwater evaporation. It also provided the context of what percentage of the total recharged groundwater pumping was via that well number. And you can see that the groundwater pumping number is actually quite small in this example. So it was a new way to actually look at the catchment water balance. And of course, we get spatial outputs like depth to water table that's been developed as a result of groundwater modelling rather than just contouring. So I'll go to the next slide. And at the same time, this groundwater modelling in the 2000s was really starting to pick up. Computing power was better. There was work done, and this is just an example, was the sustainable yields work that was done across the golden, what I'll call the Golden Broken, Campaspe and Loddon, and it was trying to calculate, well, what is a sustainable rate of pumping that can be used across long periods of time. And as you'd expect, there was always some disagreements on some of these things, but at least now it was understood what were these significant features, and those significant features is groundwater recharge. But we could still use the VAF at least as a standardized mapping layer for these estimates. Next slide, please.
The actual application of those, so presumably the rural water authorities then looked at that and came up with their allocations for.
Yes.
But then you've got all those stock and domestic bores that aren't regulated. So did you come up with some kind of rule of thumb estimate to take into account those?
Yeah. So the rule of thumb that we generally use is I'll say between, but it's usually about 1.5 megalitres per year is used by a stock and domestic well. I think some of the numbers might be 1.7. The department have got their numbers, and the different water authorities have got theirs. But as a ballpark, it's around that 1 to 2 megalitres a year usage.
Okay.
So one of the more interesting, and I do have a vested interest here, one of the more interesting, I thought, applications of those eco markets models was actually catchment tender. So that was actually trying to put an economic value on the change of land use as a response of revegetation. So there were 3 metrics that were looked at: salinity area, overland flow, and the groundwater salinity. So if we go to the next slide. The way this was done was putting an economic value on these a change in runoff, a change in revegetation. So assuming that when we change from annual pasture to tree cover, it doesn't take any stocking rates, and the economic value on 1 EC unit at Morgan, which I'll talk about later, which was assumed to be $120,000 per EC. So if we go to the next slide there, so we've got these economic metrics that we'll put on the groundwater model, and then the groundwater model was built, and then at an individual cell, so on where A is, the grid on A. Say, for example, cell 34, that recharge was changed from annual pasture to tree cover. And then B is where the change in water table responded as a result of changing that groundwater recharge rate. So then we could actually, on a cell-by-cell basis, work out which cells were more sensitive to vegetation change across the landscape. We go to the next slide, was where that was actually applied. And so we put those three metrics that I mentioned, and the way it came out was, interestingly, it was that the average cost, there was actually a net loss in productivity or economics when we put those three metrics together, but it didn't consider the biodiversity benefit. But at least it provided a framework to actually quantify what revegetation change had. I'll go to the next slide. So where are we now? 2025, 30 years on, what's going on with the groundwater levels across Northern Victoria? Okay, Richard. So I'll flick through some things pretty quick. One concept I just want to be clear is the concept of the cumulative residual rainfall difference graph. So the red line. So the red line is a trend in rainfall over time. It's a difference between the actual rainfall minus the mean rainfall. If you've got an upward trend, you've got more rainfall occurring than the average. If it's a downward trend, you've got less than average. We'll go to the next slide. So when we look at all the rainfall graphs across Northern Victoria, the green square is what we knew pre-95, and outside the square is what we know now. Ironically, in 1995, prior to that, there was an upward rainfall trend. Following that, there's been a downward rainfall trend. Now that's consistent across all climate stations across Northern Victoria and further for that matter. So we'll just keep that in mind when we look at the groundwater levels. Next slide, please, Richard. So as an example, I've just plotted here the Kundruk bore. For anyone that knows, it's just outside of Kundruk, near the Kahuna Turn. The blue line is the cumulative residual rainfall. The other lines is groundwater levels in the different hydrographs. When you plot them together, you can see that the cumulative residual rainfall also drives the groundwater level fluctuations over time, particularly in the shallower Shepparton Formation. So I'll just keep that in mind as I pass through these next few slides, Richard. So we'll go across the different valleys and I'll talk about the trends. Where the green square, as I said, is 1995 prior. I've got the cumulative residual rainfall up on the top right there. You can see the rainfall trend kept increasing to around 2000. The groundwater levels in the Goulburn have just kept on increasing regardless. Groundwater pumping rates increased in the early 2000s, but the groundwater levels have continued to rise. Next slide. In the Shepparton irrigation area, in the Campbell Formation, so that deeper aquifer, the groundwater levels started to drop off. You might question if it was a function of rainfall or the climate trend or pumping rates or a mixture of both. I think it's probably a bit of a mix of both. In the shallower water table in the Shepparton irrigation area, the groundwater levels have dropped off. Now that might be a result of the climate and irrigation efficiency. So you can see what message I'm trying to pass through here. So we'll go to the next slide there, Richard. In the Campaspe Valley, in the lower Campaspe, the groundwater levels prior to 95 in the green square were actually chock-a-block. At the surface, couldn't rise anymore. Increased groundwater pumping rates and a lower rainfall trend, those groundwater levels have decreased and now can oscillate up and down. Go to the next slide. Again, same thing in Bridgewater. You can see in the Loddon Valley, the groundwater levels prior to 95 were really filling up, didn't really have anywhere to go. Decrease in rainfall trend, increasing pumping rates, and those groundwater levels now have decreased and seem to be stabilising. So it's really interesting how in those valleys across Northern Victoria, those groundwater levels have dropped off as a result of both pumping, but probably more likely to be the rainfall trends as well. And the reason I say that is if you look at the catchment water balance, the groundwater recharge is actually a small component compared to the pumping volumes. I'm going to go across a little bit further really quickly. In the Eastern Mallee, around Ultima, the groundwater levels in the Prilla and the Renmark, they're still going up even though the rainfall trends down. And another one, please, Richard, at Patchewalla, which is near Oyen, the groundwater in the Prilla Sand just keeps going up. The oscillations that stop in around 94 are a result of the monitoring which was monthly, now back to annual. So we had a feel on what those fluctuations were. Now we can just see the longer term trend. Next slide, please. In the Mildura irrigation area, those groundwater levels have really dropped off as a result of rainfall trend perhaps, or irrigation efficiency changes in land use. And then in the Renmark group, it's also always been trending down, and I'm not sure what's going on with that last little step rise in the Renmark. But it's clear that the rainfall or the climate trend has decreased since 1995. Next one, please, Richard.
It's a pretty dramatic increase, isn't it, at the end there?
Yeah, I think there might be something wrong with the board, to be honest. I don't know. So some of these things that we've been using to better predict groundwater processes, and that's actually the site at Kundruk before they put all the new posts in, is the environmental monitoring, the computers, the GUIs, and the GIS systems, and then the groundwater modelling methods. And I'll talk about them really quickly. So go to another slide. One of the modelling methods is the use of the impulse response function. So we look at individual bore hydrographs and try and understand the processes which cause the fluctuation in a bore hydrograph over time. We call those things environmental forcings. There's a whole heap of data you can get from a bore hydrograph before you put it into a groundwater model. If the data's good, you can calculate the specific yield, you can calculate the response time, so the delay between a rainfall event and when that causes a water table rise. And you can also identify if it's not rainfall that's driving the processes, if it's something else, such as groundwater pumping or river interaction. That's just one of these newer methods that's being used. Next slide, please, Richard. And of course, the groundwater modelling side of things, groundwater model, MODFLOW 88 went forward, MODFLOW 2005, they're up to MODFLOW 6, MODFLOW USG, and FEFLOW, and the analytical element methods. So there's been quite a significant advancement of different modelling methods over the last 30 years. All I'll say on that. Next slide.
Oh, what is this one? I haven't heard of that. Analytical element.
AEM is like using the TIS equation spatially. So it's a GUI that comes up that you can use. It was developed by Otto Strack back in the day, and then Charlie Fitz made it into a nice GUI setup. So it's a method you can use now.
Okay.
Go to the next slide. So one of the major things that, and I'll just spend a minute on this, is that historically when a groundwater model was built, the groundwater model would be built via zone. So that's using I'm talking about the slide on the left here, a uniform value across an area. And those zones, you might build a groundwater model with different zones. So for example, a multi-layer model, you might have 42 zones. The picture on the left shows that these zones now, we don't use zones, we use these things called pilot points. So within a zone, we have the ability for the model to actually oscillate or vary those values across each individual point by a specified range. So that means we now have spatially continuous aquifer parameters, which is the picture down on the bottom left. So what it means though, is that from 42 zones, now we have, for example, 4,200 zones. So there's a lot more pressure on a groundwater model to actually solve these solutions. Luckily, computers have got a lot quicker. Next slide, please. Yep.
Just to be clear, I was got a little bit confused there. We used to do it in spatial areas, and you would have created a model for that whole area, and now we break that area up into a much higher resolution.
Yeah.
And but still use physically based models to compute those numbers at each of those.
That's right. So that goes into, so like there's GUIs that do this, but MODFLOW and FEFLOW have got the ability to do this.
Has it changed management practice on the ground? Knowing
I think
solution?
I think from maybe not from the broader scale models, but definitely the mining type applications, the more detailed applications, this approach of pilot points has made calibration a lot better. So thereby prediction. And I'll talk about just on the next slide about how this method is applied now. So when we talk about uncertainty models, is that we're talking about those 42 cells historically. In a simple sense, an uncertainty model is saying out of those 42 cells, so the simple approach, we hold one of those calibrated values fixed and we recalibrate the model. And we do that for each parameter. We hold one fixed, and that value is held fixed based upon a random number that you set within the range of what you think is feasible, for example, for the hydraulic conductivity of that model. Now, that's all good when you've got 42 zones, but if you've got 4,200 zones, it becomes a lot more pressure on the groundwater model to solve these solutions. But fortunately, over this same time, well, actually, I think because of this, is that the likes of John Doherty's got PEST and different methods of actually his ensemble approaches to solve these solutions. We don't have to run the models as much. You can use parallelized matrices to solve these solutions a lot quicker. Go to the next slide.
It's just interesting to reflect. CSIRO did a webinar 2 weeks ago, and they've been using AI to achieve best fit calibrations of their models. Have you sort of come across that at all yet, or it's early
Yeah,
days?
I'm a bit nervous on AI in the sense that it also lies. So I don't know if it actually. I think it's useful to help you code and program, but I'm not convinced that it'll give you a proper water balance yet. But maybe people have advanced further than me.
AI is a lot like a human, isn't it?
Yes, yes. Sometimes it tells you the answer you want to know rather than you need to know. So I'm just going to talk about uncertainty a little bit more. So just as a quick one about I'm going to talk about the concept of P5 and P95. So that is a range of values. So using statistics to present in model outcomes. So where a P50 is the average outcome. So we were talking before about having 4,200 different groundwater models and predicting them out, you'll have a range of results. So to use that information in a useful way, you can statistically present that information from a P5, P50, and a P95. So where P5 is 5% of the values that will be less than a value, and P95 is the values will be 95% of the values will be less than that value. So just statistics, just a quick refresher there. So if we go to the next slide, which is probably more relevant, we use this uncertainty information now to come across and use it as a tool to identify risk and work out trigger levels and a trigger action response plan. So the example that I've got here on the left is for example, a bore hydrograph. So where traditionally we just have that black line, which is the one value in a groundwater model. Now we use statistics and we say, here's the P5 and the P95. So it provides a range or an envelope of possible model solutions. And then if you have a trigger, for example, a GDE or I don't know, a water supply well or something that might not cope, if you lower the water level below a certain point, you can set that as a trigger. You can set those triggers either way. Now, you can do that information on the right. You can do that spatially as well. So the same context I've got here at the 50-metre AHD contour, I'm presenting the P5 and the P95. And an example is a receptor, which is the happy face or the upside down happy face. So it's just, this is how uncertainty get used spatially now. So I'm just going to that.
How much confidence do you have in those values? Just sort of interesting to look at. You showed us this rainfall data and how for 30 years things were going up, and really there wouldn't have been any predictions back then of that happening.
No.
How do you take, I suppose what I'm saying is, how do you take into account the fact that you got these sort of large scale climate change things that we're really guessing a bit about, those rainfall patterns, yet they're so significant in terms of setting something like these response levels?
I think recharge or rainfall is probably one thing that's a bit of a shortcoming in a lot of the long-term predictions. For example, MDBA have a 30-year climate sequence that is the last 30 years climate sequence, and they just put that forward in the forward projections. Now, we don't know what the climate's going to do, and to assume that the climate in the last 30 years is going to be the same as the next 30 years, well, what choice do we have? We have that, or we can pick the mean rainfall. It's a real challenge, and I think that that's actually something that should get further interrogation, considering how significant it is on model predictions.
I do know DPI New South Wales have modelled out the next 50 years. They used APSIM modelling,
Yes.
climate projection data. And they've come up with I think it's plant available water number, like at a resolution of, I don't know if it was 30 metre by 30 metre for the whole of New South Wales, right? For the next 50 years. So it's kind of impressive. But
Yes.
I was wondering if that's been taken into this sort of calculation.
Nah, look, I think recharge is it's the Achilles heel of any groundwater model in my mind.
All right.
So just as a context for people, just to understand what a trigger action response plan is that it actually uses the bounds that were defined in the P5, and that's meant to say 95 assessment. And generally you review those across a 5-year interval. So then it sets out some targets and conditions. If you don't meet those conditions, it provides responses that need to be done. So it actually provides the regulator and the proponent a clear set of guidelines to work to. I just wanted to introduce that concept.
So how does that roll out on the ground? Do we have sensors measuring in real time and keeping an eye on these things, or?
Well, it depends. I guess ideally they're sensors. Sometimes it's just people making monitoring bore runs that measure those levels that might get updated 6 months later. The important things with the TARPs are that somebody's responsible to report at a certain interval where they collate that information and actually analyse it.
And do you know if that's automated, like that actual processing piece? Like it seems like a fair burden for the State Department or whatever to be pulling all that together.
No, not that I'm aware of. I mean, the example I've got here is for a mine, and I know the mine don't have an alarm system that goes off if the groundwater levels drop to a point, but it'll get picked up in the monthly or the annual review.
Okay. It's a good system by the looks of it.
Okay, we'll go to the next one. So I'm going to go really quickly here because I know I'm talking too long. I'm just going to quickly talk about MDBA and how the EC accounting works. It started back in the 60s and 70s. It was recognised there was too much salt going down the Murray River, and the South Australians didn't like drinking salt water. So there was a variety of state and federal government initiatives. 1998, it was said, okay, we need to try and do something about this, and there was some work done. And then there was different EC registries around 2000, and the MDBA really drive this by having salinity models and updating the register and project those salinity potential impacts across the 2100, which I was talking about before, about these different climate sequences. I'll go to the next slide, Richard. It might be a little bit more digestible.
Just looking at when I was working in that area.
So some of you might have heard what Register A and Register B is. I used to be really confused what it all meant. Register A is anything that happens on land, on ground, post-1998. And Register B is the legacy of history or pre-1988. So a line was drawn in the sand in the salinity concentration at Morgan in 1988. And so it's always been from that point forward that the salinity can't get worse than what it was in Morgan in 1988, which was 800 EC. So that's where the Registry A and Registry B, the concept behind it is. Now the next slide there.
This is salinity within the Murray River.
That's right, sorry. Yes, so the water that flows down the Murray River, they measure it at Morgan, and it can't be more than 800 EC. And if it is, the states have to try and do something about it. This is where it gets very complicated. And I don't pretend to be an expert on this bit. So when I say the states do something about it, there are a variety of salt inception schemes. These locations were identified to be the significant contributors of salt into the Murray River. In Victoria, we've got Pyramid Creek, we've got Bar Creek, and we've got the Mildura-Moorbeen salt inception schemes. They all work in different ways, but the long and the short of it is that what they have to do is try and reduce the amount of salt that they're discharging into the Murray River to make sure that the salinity at Morgan doesn't increase. As a ballpark number, an EC unit at Morgan costs around $220,000. Previously, I had a number of 120. I really don't know what the exact number is. That number is calculated by the amount of on-ground work required to actually decrease the river salinity by that EC unit. And one EC unit is equivalent to 85 tonnes of salt. So hopefully that makes sense.
It does. Just for everybody, these aren't salt inception schemes, they're salt interception schemes. So they're
thank you.
We're not trying to generate more salt. I actually
good point. Thank you.
I worked on some salt interception schemes. You know, there was a couple of things. There was a horizontal well that was installed to go through a shell lag layer over in around Loxton, Bookpinong area. And a lot of numerical modelling to work out the benefits of intercepting that water as part of doing the costing before those works were done. There was a huge amount of rigour that went into it. Other areas have got bore fields, significant sort of conventional bore fields. Maybe the last thing to say was there was this fantastic study done where I'm not sure if it was CSIRO or someone else did the study, but they towed a geophysical array down the Murray River, and they could measure, and you could see the drawdown curves from the bore field where there was over extraction of the groundwater, and they're actually pulling the Murray River water up into the scheme, and they could use that to adjust their pumping rates to optimize it. But there's some really fantastic work that's been done on those schemes. That's enough from me. I will go to the next.
No, it's good, Richard. I'm not doing this justice as much as it should. I guess I'm consistent with my spelling at least. So I apologise for that.
I think that's fine.
So, I mean, this is roughly what Richard was saying about what a salt interception scheme looks like on the right there. And there are some of the numbers that we start to look at about what, in Victoria at least, what that government allocation of the EC credits are. So I didn't want to spend too much time on it, but I just wanted to acknowledge that there's a lot of work that gets done in calculating these different states' EC credits and how it gets regulated with the MDBA. And as I said, Victorian schemes at Pyramid Creek, Bar Creek, and the Mildura-Moorbeen salt interception scheme. We'll just go to the next one, Richard. I don't think I've got many left. One more. So I just wanted to present. So on the left-hand side, I've just last night downloaded some information of the Murray River salinity at Morgan, and then with the different colours squares. And then on the right, the framework or the modelling approach that the MDBA uses is a model called Big Mod, where they get all the different salinity salt interception schemes, salinity information, feed it into a model and predict what the salinity is going to be over time. And that's just something I lifted out the MDBA website last night, just as a matter of interest. So that was my summary on how the MDBA actually works and how it all links in together. No, I think that's it.
Mark, that was fantastic. Thank you very much for that. It's
My pleasure.
interesting just to reflect on a couple of things, like the interception schemes and the fact that you've got a sort of end criteria of 1 EC units is really empowering for management practices, sort of everything back from that. So, the
Yes.
whole interception schemes and the funding of it and the benefit of it, etc. I was over in Denmark at a conference earlier this year, and the EU have put a nitrate criteria on all rivers there, and it's the same sort of approach. So now they're getting forced moving back from that and putting all these management practices in place, which is, a really good thing. So it's good to reflect on that. I guess the other key reflection for me is, the climate changes, and any management practice we have needs to be dynamic, doesn't it? But yeah, really good. Thank you. We better move to the early bird questions.
Before we get to those, Richard, do you mind if I chime in there?
Oh yeah, sure. Sorry.
That was wonderful, Mark. It was really fascinating to hear someone really put together, some decades of work that's gone into a critical issue in groundwater in Victoria and indeed Australia more generally. You mentioned there, if I've got you right, you said something along the lines of recharge being the Achilles heel of numerical models.
Yes.
Yes, which I tend to agree. It's such a tricky parameter to try and understand and pin down. So perhaps I could get you just to reflect on some of the other things you were talking about there, the wonderful advancements of having technology and computing power in particular and software. Has our let's say enthusiasm for hydrogeological characterization kept up with that, i.e. drilling and sampling and these sorts of things, and additionally improved understandings of the fundamental processes in the landscapes?
Yeah, thank you. Good question. It's interesting. I didn't mention the next advancement with the groundwater modelling is that still using bore hydrographs, but the likes of John Doherty's new hobby is looking towards, he's got a different name for it, but I'll call it Fassie's uncertainty. So saying that we understand what the stratigraphy is in a bore, but how do we extrapolate that to the next point in the landscape? Does the aquifer thin out or thicken? Does the and laterally, does it vary as well? So we know that we can get a variety of answers in a single groundwater model, and how can we constrain that to what's plausible and what's not? So in a modelling sense, that's where things are advancing, but in the context of, on-field and data collection, I actually don't believe that there's much that we can do there in the sense of monitoring. We can, for example, if I have a logger that monitors at an hourly interval, I generally take that back to weekly or even monthly because the groundwater model can't run at that speed. So there's a limitation there. With respect to the limiting the hydraulic conductivities of aquifers or defining what that number is, I think us doing slug tests help, but I'm not convinced that we should just set our bounds based upon a slug test or a pumping test for that matter, because I think there's more variability in the system than we can tell. I don't know if I've answered your question there, Ben, or not.
Yeah, I was leading into the more reflection on our ability to understand actually what's really happening in these systems, and therefore, is recharge really this much or that much, and what is influencing being able to quantify it and understand it.
Yeah, I think that's the challenge, and that was where I was trying to get to with the impulse response function stuff. Because what I'll say traditionally is that anyone that wants to build a groundwater model, they just grab the hydrograph and say, look, I'm going to calibrate to that. But the reality is that there's so much information in that hydrograph that we could lift out and inform the groundwater model before we start the groundwater model to constrain those results. I think that's what should be done a lot more. So there's hydrograph analysis and having processes to understand and quantify those processes is a real area that has got a lot of scope for more work.
Excellent. Thank you. There you go, Richard.
We're expecting more, Ben. Hold on, here we go. All right, I'll read out the early bird questions. Number one, my observations over 40-year salinity extent is based on wet periods versus dry periods more than land use. Do you agree?
Well, yes, no, I'm a bit nervous how to answer that, but yes, I do think that climate is a driving factor in these groundwater level changes. I think the challenge is that we can do something about land use and groundwater pumping, but we can't do much about the climate. That's something we never had a choice, to the point that, yeah, I think that we can only do what we can deal with, what we can change, and that is the land use and the pumping rates.
It's sort of just to reflect on how long it takes. Like if you change your land use, like if you put in, if you made a decision 30 years ago and you said, oh, I need to put in eucalypt trees to draw down the aquifer, reduce recharge, like how long that would take to actually be effective. And over that time, the game's changed, the climate's changed.
Yeah.
Are there a lot of things that were done back then that would now not make sense to do because the climate's changed?
I think there's some places where people putting in tree plantations and that might not have survived perennials. Some of these perennials, they were getting into the lower rainfall areas where they're really struggling to produce enough growth. Yeah, look, there's some limitations with these things. You know, if you put a crop in and you assume a certain rainfall, if that rainfall's less than what it actually is now, there's going to be a response to what you can get out of it, or a reduced response.
All right, question number two, salinity issues under climate change. I guess we're touching on that now.
Yeah, we assume that climate change has less rainfall. Obviously, there'd be less recharge. But if climate change means we have more thunderstorms or more high intensity rainfall events, it might actually mean more recharge. So my assumption is that maybe it just means less rainfall, and what we're seeing in the decrease in rainfall over the last 20 years is what that might mean. And we can see that the salinity extent and the salt load exports at Morgan have actually decreased over time. And that's, yeah, so maybe I think it's probably less. The water tables have dropped off.
So this measurement of recharge, like are they based on lysimeter studies or are they based on other things?
Well, in Victoria, we used all types of things, talisman tubes, infiltration rings, and they were to work out where the water was going. But one of the best ways is actually, and ventilated chambers was another thing for evaporation rates. But the bore hydrograph is probably the best thing, and you put a logger in a bore hydrograph and correlate that with a rainfall event. It's probably the best way to quantify. If you know the specific yield, it's the best way to calculate what the actual recharge rate is. And that was why I've been leaning towards this impulse response function approach. So you can quantify that.
Okay. Does urbanisation affect salinity migration in groundwater?
Urbanisation does affect salinity in the sense that back in the 2000s there was an urban salinity group, and Wagga, Launceston, I can't think of, a little bit of Bendigo had salinity. It propped up people watering lawns more, even though there was hard surfaces. You still do get salinity in an urban landscape. I think that probably oscillates up and down according to rainfall as well. I'm not too sure about the migration side of things as it moves the salt. If anything, I'd expect it to flush it out if you get more runoff. Yeah, I'm not sure.
Mildura's got
Oh, yeah.
quite a big monitoring scheme.
Yes.
Number 4, what is the impact of millennium drought on groundwater across Northern Victoria?
Well, I hope I've answered that somewhat, but it's lowered the water tables. It's in most places, and you can see that there are some places where the water table hasn't lowered, but in most places it's actually caused the water table to drop off.
I think you did answer that. Number 5, what do you see as the most effective current strategies for managing areas with increasing soil and groundwater salinity?
I think it's trying to lower the water table via increasing plant water use. So the traditional approaches of planting salt bush or just having some kind of vegetation there rather than having bare soil. Bare soil is just going to increase the evaporation rates and increase the groundwater salinity beneath it.
We do a fair bit of work in catchment rehydration studies, and we'll use those. They're these large reports that used to be produced, those sort of salinity management reports,
Oh,
in
yes.
their terms. This is in New South Wales, but you sort of apply everything in reverse these days, right? So you're wanting to get more water back in the
Yes.
aquifers, you're wanting to rehydrate the landscape.
Yeah.
Do you have a view on that?
Oh, no. I do think that I can see a short-term benefit in that. I do wonder what happens over time when the groundwater evaporation starts to make a difference on the groundwater salinity. But no, I really don't.
What about Ben? Ben, have you got any comments about how we can improve managing salinity?
Salinity itself.
Yeah.
Well, as Mark's been talking about, the millennial droughts had something of an unintended benefit of making the salinity issue larger recede. So as far as improving it, not off the top of my head, Richard.
All right.
I think it's going to be one of those ones though, as we go back if we return to some wetter conditions, if you've been any experience this around other infrastructure projects, all of a sudden these things start springing out again and becoming problematic.
Yeah.
Do you think we know enough about our systems now, Mark, to be able to effectively manage the groundwater?
The answer's always going to be no there, Richard. I like drilling bores, but
What about with all these models, Mark?
oh well, then I can run it. Then you can run a model as well. It's like Christmas. But I think that there are areas that we don't know. There's a lot of gaps in some other areas. The groundwater supply areas seem to have more data, although the likes of the Goulburn there with those increasing groundwater levels, even though the pumping rates have increased, there's some questions that I have there that I'm very curious on, and why the Perilla Sand's still increasing at the rate that it is, irrespective of the climate's a bit confusing for me. So there are still more questions around. Yeah.
Number 6. What are successful ways of dealing with hypersaline waters?
Well, I think the salt interception schemes are probably the way that it's being dealt with across the MDBA. I think increase plant salt bush on it if you want to try and get something out of it. I don't know if turn it into an evaporation basin and try and get rid of it, but I'm not sure if there's much else.
They do salt harvesting. So the water they collect from the salt interception scheme, well, up near Baronga there, New South Wales, they actually harvest that salt, and I think they do that is it Pyramid Hill as well? I'm not sure now.
Is that right? Yeah, Pyramid Hill. Yep.
So there is some money to be made out of hypersaline waters. We're
Some
involved
might argue with that.
Sorry, what was that?
I said some might argue with that. Yeah.
Yeah, I don't know the numbers. The One Basin CRC that we do some work with, they run a project looking at the cost effectiveness of desalinating groundwater, because obviously there's plenty of saline groundwater around, and if it gets cost effective to desalinate it, it creates an opportunity.
Yeah, yeah.
Number 7, what are the guidelines for using water with high EC and high SAR, e.g. EC greater than 3, SAR greater than 3 applied 1:1 with the rainfall at 700 millimeters per year?
What's that, Ben? Oh, yeah, you can take it. That's fine. Yeah.
No, I'm happy for you to talk about this one, Mark.
Look, I honestly, that's out of my lane. Looking at the sodium absorption ratio side of stuff, that's not me.
You want a soil scientist? If there's
Yeah.
any soil scientists watching, they want to put something into the Q&A, that would be great. All right, so we stumped you on the last early bird question. I'm going to go to the Q&A questions now. Just got to find them. What does it do this? There they are. And I'll see if I can bring both. Not sure if everyone can see both your heads. Righto. Here we go. Are all deep leads confined aquifers?
Well, in the uplands, they're confined. Are there groundwater systems above them? Yes, in the lower parts of the catchments. In the upper parts of the catchments, they might be unconfined. That's where they get their recharge from.
Okay.
I'd say geographically, mostly they're confined. That'd be reasonable to say, Mark, across the basin.
Yeah, okay, yep.
No argument there. Okay. Next question's from Robin Madsen. That jump in the groundwater level in the Mildura area would be associated with the floods that went through there a couple of years ago. Not rainfall in Mildura, but from higher up.
Yeah, it's a hard one. Maybe I'd have to look at that in more detail. It's strange that the water table didn't jump, and that response I haven't seen in any other Renmark group aquifers in Northern Victoria. So if I see another hydrograph in the Renmark group that does that, I'd understand that. I'm just not sure at this stage. I'm not convinced that step in such a deep confined aquifer would respond like that.
Well, Robin seems pretty sure about it, Mark, so you might want to catch up with her offline.
Yes.
So just on those sort of confined systems, when you get a flood event, a long way away, is in your experience, like, do you see a pretty rapid response in the pressure within the whole system?
Yeah, good question, that one. Initially, once upon a time, I would have said no, but like the Kundruk response that I showed there at the nested site there, is that that's showing responses in the Renmark group from climate change without any significant lag time. So the lag time's in the order of maybe a week, but it's not months or years. So it seems to be very fast. So that the pressure response seems to be quick.
Yeah, I was going to say sometimes I think that's the issue. There's loading that's happening in the unconfined aquifer at the surface that's just creating that extra pressure, hydrostatic pressure in the system, and you see that the hydrograph is really a reflection of that rather than water travelling through that aquifer.
When you say loading, so what do you mean? Does you mean that the head's extended up beyond the confined aquifer?
Well, if there's an unconfined aquifer sitting in that system,
Yeah.
it fills up. That's more weight that's pushing down on the system.
Okay, so it's just driving more through.
The old term we used to use was Mark Reed used to explain, was like piston flow type stuff. So pushing from one ends up in the other.
Yeah. All right. Next question from Thomas Payne. If you have a low-lying area in the landscape, like a lagoon, that is discharging highly saline groundwater due to a high groundwater table and hydraulic gradient towards the lagoon, would keeping a permanent water body within the lagoon prevent the saline groundwater from discharging?
Might in the lagoon, but it'll just push the salt out next to the lagoon, I suspect. I can think of some examples that are politically sensitive at the moment on that one.
We like those sort of examples.
Yeah. I think you can keep flushing the fresh water into that lagoon, and I think you'll just raise groundwater levels adjacent. Ben, did you want to add on that one?
Yeah, I was just saying, I mean, you could do that. You could push the hydraulic gradient back the other way, but then you're probably wasting a lot of fresh water doing that.
Yeah. But conceptually, you can do it.
Conceptually, yep.
All right. Next question. Abel Imiraj. I recall target salinity and Morgan must be below 800 EC 90% of the time. I was working on the Warcool Talakul salt interception scheme.
Yes, you're right. Actually, that I've said 90%, but I think it's you've just said there. I was about to say yes. It's actually 95%. So yes, it's 95% of the time the EC's got to be less than 800 EC, and I think that's on a daily time interval.
All right. Next one is from Morteza Javedi. How actually effective are the salt interception schemes?
Well, they pay for themselves. They take the EC out of the Murray River and lower the salinity. I guess they are effective. I'm not too sure how to answer that.
I was interested to see you've got that power consumption column in your table.
I thought that was interesting too. Yeah.
There's a big ongoing recurring cost there. Is that, I presume that's taken into the sort of costing calculation of the payback?
I think it might have something to do with CO2 emissions possibly as well.
Yeah, I think it's the CO2 issue that they're trying to cover off there.
Oh, okay.
Yeah.
How, we've covered that one, a big button. Next question, anonymous attendee. What should a scoping statement for a modern day hydrogeological assessment look to include? Ben?
Yeah, Ben, maybe you start with that one.
It's a pretty nebulous one, and it depends on your objective. But let's assume it's a salinity investigation of some description. Mark's done a really nice job of showing some of the data sets that you need to have at your hand. So soil types, geology, these sorts of things, which are all pretty readily available. Then at some point, you're going to need some site investigation. It's going to include some drilling, particularly into the water table, and understand depth to groundwater, how salty the groundwater is, and where that groundwater is moving to. And such, then you can start to address potential risks of whatever the activity is that you're concerned about. Just as a very general overview, Mark.
Yeah, I think that a scoping statement, you probably should think about it in a step process. So one, by looking at what data is available, then what data you need, and then what you think is realistic to actually do in the assessment, depending what you're trying to work out.
Do you think
so being really clear up front about what is it the question you're trying to answer, or what is the objective, and being really clear about that.
Yeah.
Do you think with all the detail we've now got with these management areas and models and that sort of thing, that the need for assessments is going to decline and we'll just rely more on the models?
No, actually, now my previous work in government was more regional scale work, and I've noticed the resolution of work now is really increased, and it's very much site specific, and the regional work is less common. So that amount of the requirement for detail for sub-meter accuracies, I think it's actually increased. Yeah.
It's interesting to look at the how variable the, for example, soil hydraulic characteristics are. When I did that work in Western Australia, that became sort of a limit to how much you could do, right? So
Yeah.
in the end, I reviewed all these models and sort of set it on a black box model and said, well, given the lack of awareness of the variability, mucking around with a physically based model may not make much sense. There's certainly holes in some of the data, I guess.
Yeah.
This is from Robin Madsen, is there any work that shows that replanting up to 30% of a farm that brings farm productivity increases is significant enough to help lower the water table?
Yeah, it's probably going to be on a site-by-site basis there. I mean, if you're in the Upper Wimmera and you plant 30% of your farm to trees to stop lower the water table, there might not be much benefit, but 30% of your farms at Kundruk, you might not be able to put 30% of your farm under water table because they'll die from salinity, but yeah, it will lower the water 30%. Yes, it will lower the water table planting trees. It's to understand there's a scale issue to deal with there too.
We've done a lot of work directly measuring tree water use, and the numbers are quite staggering how much water trees do pump.
Yeah.
And the CRC for catchment hydrology have got some published numbers on, well, you'd have to find their records that the CRC doesn't exist anymore, but
No.
those numbers, but I think it was like for a mature eucalyptus regnans, it was like 800 litres a day or something. It was a massive number.
Yeah, okay. Yeah.
All right, next question. Anonymous attendee, there are some studies on renewable solar energy for salt interception schemes, and CSIRO did an energy optimization program. That's good to know.
Okay.
And the last question from Kieran Harford. Could Mark elaborate on his comment regarding slug and pump tests?
But yeah, I think particularly in these site detailed investigations, the slug tests and the pumping tests, they're the only point of truth that we have on an aquifer parameter besides bore hydrographs. So they're very handy things to understand. And you know, in the last 20 years, it's actually been it's a standard approach that people are now using to provide a parameter on an aquifer, rather than just looking up a published reference and to say, you know, hydraulic conductivity is 1 meter a day in the Prilla sand. Now people will do a slug test on site and find it's 0.2. So I think that they're very valuable on detailed site investigations. The cost of a slug test is obviously a lot cheaper than a pumping test, but a pumping test will provide more information. Now I know that Kieran's got an approach that sounds like it's a mix between the two, and I'm trying to get my head around it a little bit, but it actually does sound quite promising what he can do with his automated slug test approach.
That was the one that was at the IAH
Yeah.
exhibitor area. Yeah.
Yep. Yep.
Well, that's the end of our questions. So thank you both very much for your contribution today to sharing knowledge. I thought that was an excellent presentation. And we're planning on doing some more joint presentations with IAH in the new year, but that's the last webinar for the year. Thanks so much for everyone who's attended over the year. It's been fantastic level of involvement, and thanks to IAH for collaborating as well. So thanks very much, everybody.
Thanks, Richard.
Thank
Thanks,
you.
Mark.
Thanks, everyone.